All right, that screen somehow doesn't drop down. Well, you can manage. As a matter of fact, I think the university has a general peer mentor program, right? So that's open to both female and male students. Sorry? I believe that in university there's a generic peer mentoring program. It's a student-led program, actually. So that's open to both male and female students, right? It's not a highly, made use of program. So last year, the school engineering, a bunch of faculty actually volunteered to go to the first year. Well, actually, your cohort, right? Only 3 times during tutorial hours, trying to provide some guidelines, mentorship. So that's more of an initiative within school engineering. Okay, as again, it's not a very organized program, but there definitely more things can be done. Okay, let's get on with the convolution, and then I'll show you a little bit demonstration afterwards. Okay. So as a matter of fact, often in time, if I have time, the first thing I would ask you to do is use 1 minute to write this formula for as many times you want. 1 minute you could write maybe 20 times. Why do you do that? And you'll memorize that. Okay. So use 1 minute of your daily time to write formula, not just this one. If there's any formula, okay, just write it as many as you want within 1 minute. You never know. The more you write, somehow you actually will get, some kind of inspiration. Yeah. Okay, we'll finish the example we did from previous example, per previous lecture. We had a f of t, which is a box like this, and g of t, it's a smaller size box. And we're trying to convolute these two signals. Okay, and then we'd used graphic approach. So graphic approach basically means we change this to tau. So nothing else but just change this to tau. And then we also change this to tau. We'll try to get from g of tau to g of negative tau, from g of negative tau to g of negative tau minus t. Because this is g of t minus tau, which is what's needed in the integral, okay, for the convolution. So following this step, we get basically g of t minus tau, which will be a box again. And this side is -1 plus t, and this side is t. Okay. So that's the two graphs. Okay. And we need to multiply these two graphs together, right? Because that's what's needed within this convolution. And then this is where we started to basically look at the patterns of the multiplication. Right? There are many different patterns. The first pattern, as we noticed, is when the box is completely on the left side of the plane. So this is the first pattern. So for this pattern, right, this is your pattern number 1. For this particular pattern, the multiplication of these two graphs basically give a 0. And then the next logic step is for this pattern, what would be the range of the t, right? Satisfy this pattern. So in this case, it's quite easy. So because you want this edge here to be on the left side of this tau equal t equal to 0 here. So basically, when t is less than 0, right? That's for the pattern number 1. So when t is less than 0, your f of tau times g of t minus tau will be 0. In other words, your integral, right, will also be 0. Okay, so that's pattern number 1. Pattern number 1, when t is less than 0, we get integral 0. Yes? I can't. There's some mechanical problem. Yeah. So, a student on this side okay to look at this? Okay, yeah. I'm sure IT is on it. Okay, that's the first pattern. And the second pattern, the second pattern is when g of t minus tau is in this kind of a location. So hovering both sides of this system, okay, one side on the left and one side on the right. So that will be more or less like this. Your coordinates of the two edges will not change, it will still be like this. Okay. The reason we're using this pattern is because I will use the green one to redraw this f of tau here, f of tau. Okay. So now in this pattern, let's call this is pattern number 2. Okay. So in this pattern, the multiplication, right, of the two graph, okay, will be this part of the green times this part of the red, right? So only this portion, right? Because that's the only portion overlapping both of the curve. Other than this portion here, multiplication over this range will be 0. Multiplication over this range will also be 0. So I guess the first thing I should do is for what range of the t that you will have this pattern, right? So what you do is you have -1 plus t must be less than 0. So that'll guarantee that this edge is on the left side of the 0 axis here. At the same time, you want this t to be greater than 0. So that'll guarantee that this box will hover both sides. And together, you end up with t greater than 0 less than positive 1. So I can use equal signs, okay, all the time. That's fine because it's going to be a continuous. So you can use equal signs. That's okay. So this is the range of the t will give you such location of this box. And the multiplication, right, basically you see that will only be non-zero for this range of tau. So that's the tau here, tau from 0 to t. So now you can do the integral now. So we're integrating f of tau and g of t minus tau. Since we're only care about the non-zero part, so I only will care about the tau between 0 to t, right? 0 to t. That's where you will integrate. You're integrating the multiplication of these two functions. And the multiplication of the two functions within 0 to t is 1 times 1, which is just 1, right? So that gives us a t. Okay. So now if you recall in the previous lecture, at the beginning of the lecture, the nature of integral give you the area underneath the curve, right? So in this case, what is the curve? It's this multiplication. In this case, if you multiply this out, you get this. So the area underneath that multiplication is this shaded area. So this shading area really depends on the variable t here, because this box is still moving, right? So the more it moves to the right, you can imagine the area will become bigger and bigger, right? Until when? Until maybe the box becomes this. Okay? So that's why you see the area T here is going up. Okay, it's going up. And that's what actually the next pattern will be, right? So the next pattern here is when g of t minus tau goes to the right side, and again the f of tau is like that. So this box move to the right side and reside inside this f of tau box. Okay. So that's the pattern number 3. And for this pattern, first thing is, what will be the range of the t such that this box will be on the right side of this plane and will also be within this f of tau box, right? So how do we find that information? So we need -1 plus t, this edge, greater than 0. We also need the t less than 2. So altogether you get t less than 2 but greater than 1. So when t is within this range, it's guaranteed that this box will be within the f of tau box. So now you can do the integral here. You integrate the multiplication of these two curve or these two function. We are multiplying nothing else but the overlap region. In this case, the overlap happens always from here to here. So always happen between -1 plus t to t. And the multiplication between the two function, right? The multiplication between the two function is 1 times 1, which is also 1. Okay, which is also 1. And this is simple, so upper limit minus the lower limit, which equal to 1. Right. So let's go back to the concept. Remember what I said? The integral gives you the area underneath the curve, right? And this is the curve, the multiplication. The multiplication, when you multiply these two out, you get this. And you look at this box, the area of the box is always what? 1, right? It's always 1. And that's what you get here. That's 1. Okay. And the last pattern, not the last pattern, the next pattern is when your g t minus tau covers across this edge, tau equal to 2, cover across this edge here. So it does not completely reside inside this box anymore, so it goes, part of it goes out of it and part of it still within it. So then in this case, this is the area now, right? So area should start to decrease. So this is constant and start to decrease. So what guarantee this location then? It's -1 plus t less than 2. Okay, so less than 2. And then t will be greater than 2, this side. So altogether you get t greater than 2 but less than 3. So when t goes to this range, the g of t minus tau will be at this particular location. Then the integral for f of tau times g t minus tau, the range of the integration, right, it will be the range where the overlap happens. And that's from -1 plus t to 2. The multiplication of the two curves within this range is always 1. So this is a 2 minus the lower limit. You get 3 minus t basically. Okay. So that's the third. This is what pattern is? Pattern number 4. Okay. The last pattern is when the box completely moves out of the range of the overlap. Okay. So in this case, of course, it has to be. Oops. Okay. Okay. So 3 minus t, right? And that's when -1 plus t is greater than 2 or t greater than 3, and the integral will be 0 because the multiplication is 0. Okay. Alright, so that's the end of it, right? 5 different patterns. Okay. 5 different patterns. At the end of the calculation, you need to summarize everything together. Okay? Summarize it. You put all the information together. Basically means, yes. This is the generic integration, right? Yeah. So it doesn't matter anymore, actually. Yeah. So you don't, for the last one, you don't actually need to write anything at all. So the first thing is you get 0 when t is less than 0. And then you get, the next is you get the t when t is between 0 and 1. And the last one you get a 1, the next one you get a 1 when t is between 1 and 2. And then you get t 3 minus t when t is between 3 and 2 and 3. Then you get back to 0 when t is greater than 3. It is a continuous one, okay? You can literally see, for example, when t equal to 1, you substitute the 1 here, you also get the 1. When t equal to 2, you get 2 here, 3 minus 2, you get the 1, right? Yeah. So you can graph this convolution. Okay, you can graph this convolution. That's the result. So when t is less than 0, it's 0. When t is between 0 and t, which is what? in 0 and 1, you get a t here, right? This is a straight line t. When t is between 1 and 2, you get 1, constant 1. When t is between 2 and 3, you get 3 minus t, which is actually this. So that's the sort of the and that is the evolution of this convolution as t changes, right? Which represents, as we said, the area underneath f of tau times g of t minus tau. Yes?
One more time, why in part 2 and 3 for the f tau times t minus tau is also
equal to 1. Yeah, good point. So let's go back to pattern 3 and, well, let's go back to pattern 3 here. Okay? So in the pattern 3, the overlap happens between -1 plus t to t. So when you do multiplication of two functions, so you basically multiply everywhere together, right? So for example, maybe you say, what is the value of the multiplication at this moment? So what do? You basically look at the value of one function and then look at the value of the other function. You multiply them together, right? And obviously this is 1 times 1. So it doesn't matter which moment you pick between this overlap range, the multiplication is always 1. That's why the integrand here becomes 1 at here and also 1 at here. Good? Okay? So in summary, this is what happens to the convolution. I do have a MATLAB animation that you could use to help you understand the process. I'll upload this one here. There's also video associated with this example. Okay, well, let it start up. Now, you probably have noticed the examples we have gone through, okay, involve a piecewise function. Okay. Can we be a little bit quieter? Okay. So it starts up here. Okay, so observe this transition of the convolution here, okay? It's the blue box is the g of t minus tau. And it's moving to the left, to the right as t goes up. The bottom line is the results of the convolution. So you can clearly see the different patterns, different overlap, resulting in different values for the convolution. Okay? Yeah. So make use of this to help you understand the interim process of the convolution. All right? Yeah. So there's it doesn't come out all of a sudden out of blue. It's actually step by step, right? There's a process there. Okay. So you'll see that on Canvas, okay? And there's a video associated with that. Okay. All right. So let's talk about the next topic: unit step function. Now, many things that we have done so far are piecewise function. For example, we said, okay, we have a function f of t, which is e to the power negative 2t when t is greater than 0, and 0 when t is less than 0. Right? So we had done convolutions with respect to this graph, and then we did another one. Right? You write the piecewise function like that. That's no problem at all. Okay? Yeah. But we want to actually introduce another function called the unit step function, such that instead of writing function, especially piecewise function, like in this pattern, in this manner, we'll write it, okay, as a generic expression. You know, like you see, x plus y plus 1 or x plus x squared. So single expression instead of writing it piecewise like this. Okay. So first, let's look at the definition of unit step function. For unit step function, the definition is we use u of t to represent its symbol. It is 1 when t is greater than 0, and it's 0 when t is less than 0. So that's called a unit step function. So what is it unit step then? You can sketch this u of t. Okay. When you sketch this according to the definition, right? So when Dr. Trudy Kavanaugh here, you know, when she actually says, it's frustrating to hear all the noise. I feel a little bit embarrassed because, you know, we're engineering students, right? And she's promoting the mentoring opportunity, and then at the same time, the people chit-chatting, interrupting her talk. So I don't think that's a good sign as professionalism. And you know, in a class, the basic behavior as a respect is a mutual respect is you know, no interruptions, right? So I hope in any occasion, you know, whoever's speaking at the podium, you may not realize that your conversation with your friends, you feel maybe it's just quietly, but it is actually, when it adds up, it is actually you know, interruptive, right? So I do hope everybody in the future give a little bit of attention to this, right? Especially in this kind of environment. Okay? Because we're engineering student, part of the training is professionalism, and this is the professionalism I think is specifically referring to. Okay? So if I sketch this unit step function at here, okay, according to the definition, when t is less than 0, there's nothing here. When t is greater than 0, there's all of a sudden there's a jump. It jumps all the way to value of 1 at here. Okay? Yeah. Now in some textbook, okay, essentially this is what we call a discontinuous signal. Why is it discontinuous? Because it goes 0, it goes 0, 0, 0, 0, 0 up to here, right? And then jump to here. Okay, so technically it's the red portion. Now, at the t equal to 0 at the bottom here, you actually do not have anything. You put a circle here, you represent there's nothing at the bottom here. And it goes up. There's a 1 in here, and then all the way to the right. Okay? That's more precise sketch. But if you use an oscilloscope, for example, to observe a unit step function, the oscilloscope will not give you a circle at the bottom. The oscilloscope will actually just give you this. Okay. So in the future, when we draw this unit step function, so instead of this precise sketch as what I did here, so most of the time we will just sketch it like that. Okay. But you need to bear in mind that there is this discontinuity at here. Okay. So what do we use this unit step function? Okay. There are many different applications of unit step function. In this case, we're going to use it u of t to express a function, a piecewise function like this. So let's come back to this piecewise function here, right? This piecewise function. If I don't want to express it using like this format, I could actually now have an alternative way to make use of this unit step function. Okay? So I will plot, okay, for example, I'm going to plot another function at here. I'm going to plot the g of t, for example. And this time I'm plotting g of t as a generic exponential decay function e to the power negative 2t. Okay? Yeah. So there is no constraint for the t. T goes from negative infinite to positive infinite. Okay? And that's the curve like that. So now let's do a manipulation. Let's multiply the top curve with the bottom here. So multiply the unit step function with this exponential decay function. See what we get. Okay. Multiplication, as we always saying, is you multiply everywhere together, right? So in this case, everywhere over here is 0. So when you multiply 0 with everything over here, you always get 0. So basically, if I draw the multiplication at the bottom here, okay, so let's call this a g of t times u of t here. So I get 0 everywhere at here, so I don't need to draw anything. Or you can just draw a 0 along the t-axis. And when t is greater than 0, you have constant 1 everywhere over here times this portion at here. So basically you get, from here you get this, right? And this part of the curve is still e to the power negative 2t because it's 1 times that, right? Yeah. So now you look at this. This is exactly what? This is exactly that function over there, right? That's exactly this function. So basically what happens now is the f of a t basically can be expressed as e to the power negative 2t times the unit step function. And what's convenient is you don't need to specify the range of t, for example, t greater than 0 or t less than 0. In this case, the t is actually what? Can be anywhere. Can be negative or can be positive. Okay? So you don't have to specify the range of the t like this anymore. Okay? So the multiplication of unit step function and an arbitrary function, it's like you're cutting off the rest of the left side there and only keep the right side. Okay? So that's simple application of unit step function, right? And let's look at a couple more applications. But before we do that, okay, I want to show you another one here. Okay. Let's say this is the f of t, and this is a function that we have actually used in the exercise example of the convolution, right? In that we call it g of t, but anyway, that's okay, right? So it's a box, okay, f of t here. So the question is, if I express this f of t, I will say that, okay, f of t equal to 0 when t is less than 0. And when t is greater than 0 but less than 1, it is 1. It will become a 0 again when t is greater than 1. So that's how you would express this f of t using piecewise information. Now we learn unit step function, right? Can we express f of t using a much brief and short expression? Okay. So here's the idea. I will draw u of t at here. So this is u of t. At the same time, I will draw another one here. So I will call this as u of t. At the same time, I'm going to draw u of t minus negative u of t minus 1. We could draw this one here. So first of all, what is u of t minus 1? That's right, you shift this to the right, right? Which will be here. And then negative, you will flip it, right? Not flip it around the t, but mirror it around the t-axis. So it becomes this. So this is your u of t negative u of t minus 1. Okay. So why do we do this? Now because now if I look at these two graphs, and I'm going to add these two graphs together. So this plus this, or this minus that. Okay. So let's adding the two graphs together. Let's see what happens. For anywhere, this is 1 and here. This is number 1. So for anywhere that the t less than 1, it's always 1 minus 0, right? 1 minus 0. So all you have left is, so I'm going to put this down at the bottom here. Okay. So within 1, you left with 1 minus 0. You have this portion left. And beyond t greater than 1, you have 1 plus negative 1. Right? So this portion is negative 1 here. And 1 plus negative 1 is 0. So basically, for anywhere beyond t equal to 1, you have always a 0. And this is exactly your f of t, isn't it? Right? This is your f of t. So basically now I can see that f of t equal to u of t minus u of t minus 1. So what we just did is we used the basic unit step function to create a box. And this box can be a cookie cutter. If I use this box to multiply anything else, guess what's this box gonna do? If you use this box to multiply with anything else, any other signals or functions, meaning, for example, maybe I have a function like this or this, whatever, right? And when you multiply this box with that curve, with that signal, it will cut out everything everywhere else except this portion, right? Except this portion. So that's a useful one here, to create a cookie cutter using the u of t, the unit step function. Okay. So, for example, okay, I'll show you an example right here. Suppose that we have a function f of 1 of t like this. Okay, so this is f1 of t. Again, it's a piecewise. Everywhere else is 0 and goes up, down, okay, like that. And this portion here, apparently because it goes t equal to 2, vertical axis is also 2, so that's more of a straight line y equal to t, right? Okay. How do I express this f1 of t? Instead of using piecewise expression, how can I express this using the concept that we have just learned, using unit step function? Okay? So, for this f1 of t, it exists only between 0 and 2. If I can use a cookie cutter to cut out just this portion, right? Then I get f1 of t. We actually just created a cookie cutter here. And that cookie cutter, but unfortunately that cookie cutter here only up to t equal to 1, right? So if I want to this one, this is up to t equal to 2. So now guess what? I can use, because literally you have this portion is t here. But I don't need it, I don't need all of them, I only need this portion. So I can use t times what? U of t minus instead of 1, 2. Right. Now this time, this exactly will give you this f1 of t here. Yes? The whole bracket here, u of t minus 2. So what's your question? Yeah. No, you don't need to multiply 2 anymore, because this is t here, right? This is a t minus 2. So if the cookie cutter is over here, so that naturally will include that 2 there, right? So it'll cut out that portion basically for you. Yeah. Okay, so let me finish this. Well, don't have time anymore. Any question on this part? Okay, so I'll finish this next lecture. Thank you. Don't forget to go to your tutorial next week for quiz number 1. Okay.